All right. Hello, everybody. My name is Erik Ekstedt, and I'm here to present me and Gabriel Skantze's paper, Projection of Turn Completion in Incremental Spoken Dialogue Systems. So, a brief introduction. We are interested in turn taking, a fundamental conversational behavior where humans organize who is speaking when in a conversation. Now, for the purposes of this work, I'm just going to assume that a response should always be generated after a turn completion point or moment. And that is simply a moment in time after a speaker is completely done with their turn. Of course, it's easier said than done to find and classify these in practice. Now, as humans, we interact very fluently and exhibit fluent turn taking. And by this here, I mean that we take turns without long response delays and without frequent interruptions or cut-ins. Now, a typical response time in the English language is around 200 milliseconds. Of course, a response could be very much slower than that and faster than that, but typically around 200 milliseconds. Now, it's interesting that our speech production system seems to be quite a bit slower. Namely, it takes around 600 to 1500 milliseconds to prepare and execute speech. And it's interesting and has been coined the core psycholinguistic puzzle, namely, how can we have so fast response time when our speech production systems are so slow? One answer to this could be that humans use projection, or humans project upcoming turn completions to perform this fluent turn taking. And this means to imagine the future of the conversation in order to prepare in advance, such that you can have faster response time. And this is the general idea of what we want to do for a conversational system, use projections. Okay, so what we do in this paper is that we investigate whether turn completion projection is a viable option for conversational systems, and we focus on the textual domain. And in one sentence, what we do here is that we estimate the future probability of turn completions by sampling from a language model, which controls the turn-taking actions of a spoken dialogue system. So at the very core of this experiment is the conversational system itself. We have a setup where we have the system interviewing users about past travel experiences. We implement a simple dialogue managers, which have predetermined questions. And we argue that while the dialogue manager is simple, we can still get challenging turn-taking moments when the users think about their experience and remember and answer the questions and so forth. Now, our system is incremental and implemented in the Radical framework in Python based on earlier work of Schlangen and Skantze. And this conversational system has some simple behaviors such that it can be interrupted. And if it is, it will repeat that question at the next turn. And if the user provide a very short response, we ask them to elaborate. Now we're going to have one baseline, which use automatic speech recognition or ASR for the turn taking. A kind of hello world SDS if you wish. You have a dialogue manager, you use some ASR, which process the speech, and when it's done, you take the turn. Now, this is in contrast to the projection model, which is going to estimate the probability of future turn completion. So how does this work? As mentioned, at the core is a language model, which models a probability of a word given the sequence before. So if you have the string, the cat sat on the mat, provided to a language model, it might give you a high probability of the word mat. Now, our model is a conversational language model coined TurnGPT, presented at findings of EMNLP 2020. And this is a transformer model trained on conversational datasets. And for this experiment, we used 7 freely available datasets with an average complexity of 17.6. Now, the details for this specific conversational language model is not important, but it utilizes speaker tokens to identify which words belongs to which speaker. But I'm jointly going to refer to them here as a turn completion token. And a sequence to this particular model would be turn completion token, hi, how are you, the words for the first utterance, turn completion tokens, and the following word, etc. Now, if you use this, you might provide the string hi, how are you, and get a high likelihood of the turn completion token out. Now we note here that we do not fine-tune this TurnGPT model on the specific domain data of the experiments, shown by the high complexity of around 80 for the recorded data, which is just in slight contrast to most common approaches where you have a setup, you have a task, you train all your models on that task and evaluate on that task. In a sense, we're trying to use kind of a generic language model to see how well you could do without having to fine tune on any specific data. All right, so how do we actually do the turn completion estimation? Here to the right, you see that the agent said, how long was your trip? And then we have the user currently recognized user text. I'm not sure, I think it may have. Now, assuming that we have a projection point here, a moment in time where we want to make the projection, what we do is that we sample n continuations of m tokens long from the system. Here, the system projects that the user might continue with, it may have been a week, been about 2, etc. Now, you simply count how many of these turn completion tokens that you sampled, divide that by the sample size to get a value lowercase r. Then you compare this to a predefined threshold ratio, capital R, and if it's strictly below, you continue to listen. You get some more text from the user, and you reach another projection point, and you want to do the projection. It's the same thing, but here we might sample more turn completion tokens. You count them up, compare them to your threshold, and if it's equal to or greater than, well, you're going to take the turn here. Now, you have a third option where the user might be completely done with everything that they're going to say right now, but your model still wants to listen. So in order to avoid being silent for eternity, we have a fallback silence threshold where we always take the turn if we reach this. In table 1 in the paper, we have the parameters for this particular projection model. First, let's focus on this IPU value. So we define IPUs, or interpostal units, using a local voice activity detection system. And IPUs are speech segmented by at least 200 milliseconds of silence. And at the end of these IPUs, these are the projection points which we are going to project in this experiment. Now we use the turn completion ratio, capital R, of 0.4, which worked well in initial testing, and the fallback threshold was set to 1.25 seconds. Then we have the parameters for the language model. So we have 10 as a sample size of this possible continuation, and we project 3 tokens into the future. So if we apply this and have an interaction with the user, you might get a transcript like this, shown in the appendix of the paper from an actual interaction. Here we see green S's and red H's. These indicate projection points. And green, the model wants to take the turn, and red, it wants to listen. Focusing on this first here. So in this situation, we recognize we went there by. This is the currently available text to the system. And we reached a projection point. So here we projected from this moment in time, and the model said, I want to take the turn. After the fact, the ASR was actually had completely recognized the last word, and we got that after the projection moment, shown in blue as airplane here. And the same is true for this utterance. Now the third utterance shows a lot of these projection points where the model wanted to continue to listen, but we note that it erroneously tried to continue to listen after the word pizza. That is reaching the fallback policy. Okay. The experiment we conducted had 10 participants having 2 interactions, one with each of the systems. We used 2 sets of paraphrasings of questions, and we performed this over Zoom. So we connected the conversational system to the local Zoom client, but recorded everything from inside the conversational system. Upon completing these 2 interactions, a user was presented with a graphical interface where they could re-listen and then annotate where they felt interrupted. So after these interactions were completed, we can extract the result. Now again, we're interested in fluent turn taking, that is low response time and low cut-in rate or interruption rate. And we note that baseline had an average response time of 1.03 seconds and an average cut-in rate of 8%. Now the projection model has slightly faster response time of 0.8 seconds, while a higher cut-in rate of 13%. Looking into the histogram in figure 2 over response time, we see that the projection model shows a very bimodal distribution. Namely, you have these fast response times when you projected to take the turn, and a lot of slow ones after the fallback threshold here. Now, a problem with this particular data is that the fallback threshold is quite a bit slower than the actual baseline, giving the sense that the average response time of the projection system appears slower than what it could have been. Another problem is that you're simply left with these two specific values for both of the model, and it's hard to figure out how to directly compare them. So in order to tackle these two questions, we performed an analysis. And the analysis is based on the fact, like, what if the fallback threshold had been shortened? So that is, we define a maximum response time threshold for both of the systems, and imagine what would have happened if we had this maximal response time threshold. So we compare it to the silences in the recorded data and see where you would add cut-ins and lower the response times, etc., and recalculate these averages. Now, to show how this is done, here's an example, two independent examples here with green utterances are green boxes are utterances from the user and the blue from the agent. And we have time on the horizontal axis here. So if we imagine that we would have used a very long threshold on this data, we compare it to the silences and see that none of the silences are actually longer. So nothing happens here. However, if we choose a threshold that is sufficiently short, now we have to compare them and change what would have happened here. In this particular moment, in between two user utterances, here we would actually have taken the turn erroneously with the model, introducing an extra cut-in. At these locations, the agent was actually speaking afterwards, but here we would have reduced the response time it would have taken. So you do that for varying amounts of threshold, and then you can plot the values in a graph shown here in figure 3 in the paper, where the baseline values are red and the projection values are green. Now, the good thing about this analysis is that now we have a way to directly compare them. Where both these lines are defined, you can directly compare these two models. And we note that the projection curve is strictly lower than the baseline, indicating that it performs better. So, for instance, the largest cut-in rate difference happens at around 0.48 seconds. So given that you want to have a system that has an average response time of 0.48, you will be this much better off using the projection model. Right, so we estimated the future probability of turn completions through sampling a language model, which then controlled the turn taking of a spoken dialogue system. And through this analysis here, we've shown that the projection models seem to work better than the baseline, indicating that it is a viable technique for conversational systems. Again here, I note that we did not fine-tune on the particular data. So we just used a generic conversational language model and made these projections and still got this result, which is interesting. Now, of course, there are many things that you can improve here, particularly looking at the language model. You can train on the domain-specific data and increase the sample size and so on to better estimate these future turn completions. Of course, in turn taking, audio and the prosody of the voice is hugely important, so you could add those features in there. And you can spend time searching of your hyperparameters to find the best model for the best task and the context and everything like that. However, one important thing is that you would want to make more projections, such that you can do it after each recognized word, perhaps during the user speech, so that you can perform overlapping turns, etc. And another interesting thing to look at is to check how well does the projection model actually recover the actual words. That is, to what extent could we use it to actually fill in missing information during the projection time, at the projection time. So many things that we could do better here, but we think that projection is going to be more and more common to see in conversational system and turn taking. And by that, I thank you very much for listening. Bye-bye.